All right, so this is lecture 15. As you can see that last time the lecture was 13. There was no lectures on the midterms, and I promised to record it, but then I realized this is one of the important topic for finals, so I don't want to keep it as a recording. I want you guys to see this in person. So if we by chance we record anything, we'll record at the very last class, which is not part of the final anyway. That way you have ability to, you're not affected by recording of the class. If just in case we are behind syllabus. I still think we will not be behind, but just in case. All right, so this is lecture 15 again. Don't look for lecture 14 because that was exam. So this is the way you know which week it was. So I have not started grading yet. I'll grade by Friday. So that way you know your grades by Friday and for the midterms. I'll also release a survey about midterms because I really want you guys to provide feedbacks on how you experience solving the midterm questions or any difficulties. The reason is final will be very similar to midterms, the same process. You'll get 24 hours or longer for the finals. You'll have a similar question structures. You may get one extra questions because final is 3 hours as opposed to, I mean, typical final is 3 hours. But if I may set the same type of, 2-hour questions. Homework 5 is released. I didn't release it. I am still updating it. That will be released today. It's due on next Monday. So there are 2 more homework remaining, including this. Those 2 homeworks are relevant for your finals. So all you have to do is look at these 2 homework for the finals. And finals are not cumulative. So that means in everything you have done before midterms, you don't have to, at least, don't worry about those long questions. Even short questions, you don't have to worry about it, but there are certain topics that keeps coming. For instance, wastewater treatments, you are going to use BOD concept. So that means BOD itself is part of the question. Okay. So unless there are reused in this topic, you don't have to worry about those. For instance, redox. Redox is part of the question because redox is something you keep using in even the topic covered after midterms. So I'll get to that. I'll also give a list of things that you just to avoid confusion, so that you know what exactly to read for the finals. So homework is released today, so that's due on next Monday. So it's a 1 week you get. If you need extension, obviously you can always ask, but you already know how to solve those questions. We solved it last week. Okay. I just didn't release early because I don't want to think of homework during exam. Okay, so so today the class is wastewater treatment. In fact, 50% of the environmental engineering problems are related to this. Okay, because we start living in urban areas. 50% of the world population lives in urban areas, and urban areas means you have lots of water that you have to use it. And then many of the cities, at least in developing countries, all the cities have wastewater treatment plant to treat that water. Now in future, you cannot really use, you'll run out of water for big cities. For instance, in South Africa, there was a city, Cape Town, that ran out of water a few years back. In Los Angeles, if you don't use recycled water or wastewater, we will also run out of water. So that's why wastewater treatment is a very integral part of sustainability in big cities. Okay. In fact, many developing countries like India, not all cities have wastewater treatment plants. They are just release everything into sewage into river. So this is still, even in 21st century or so, wastewater treatment plant is designed in 1970s or before that. So that means even after 50 years, there are cities that do not have basic wastewater treatment plant. I will talk about what is basic. There are primary, secondary, tertiary. I'm talking about just primary, and primary and secondary. Those are the 2 minimum requirements to treat wastewater. So that means there are lots of pollution associated with wastewater treatment, not having wastewater treatment. in urban areas. So what we'll learn is basic things about what is wastewater, how you treat them. You already learned those concepts except one, biological wastewater treatment, that we are going to learn today. But everything else you kind of learned in the drinking water treatments. So there is this YouTube video. If you watch that 5-minute video, you'll know the basic of wastewater treatment plant design. So I'll not play it here. Watch it whenever you can, because I want to really solve the example problems that we associate with your finals. Okay, so as I said, wastewater treatment plants, what we focus in this class is mostly municipal wastewater treatment plants, like big cities. But there are many other, that's domestic, okay? But there are industrial wastewater treatment plants. For instance, all the, let's say Coca-Cola company or any chemical company, they have their own wastewater treatment plant. The reason is their waste, every industrial process use water. So how do they deal with that water? That could be industrial if the specific chemicals are there. Those designs are very different because those are very specific to types of waste they produce. Okay, so we are not covering that. Agriculture wastewater, normally they are not treated like a specific wastewater treatment plants because it's a very diffuse source. You are not going to collect water from like miles and miles of our land. So what they do is they design natural system like wetland. But the concept you learn here is also applied in those designs. So that's why I put it here. And mostly agriculture wastewater treatment plants, you are looking for nutrients. This is high concentration because they apply fertilizers, nitrogen, phosphorus. And if it is dairy industry, then it is a then you are looking for also pathogens, antibiotics, growth hormones, because these are things that's given to your all the chickens or cows. So those has to be also treated. Hormones. In domestic, by far the thing that you have to treat is BOD. Okay, that's the main goal, remove BOD. So that's why you know the concept of BOD. Now we are going to apply for wastewater treatment plants based on the reaction you see in the wastewater treatment plant. So again, as I said, why we need to treat wastewater, you know that there are two reasons. First is water sustainability in urban areas. We cannot have enough water in future because we are buying all this water from outside and then we are wasting it. And we can't keep buying because the population will continue to increase. So that's number one. And then also, of course, the pollutions. And these are different, as you can see, most of the wastewater treatment plants, they give you what is there. This is very standard. They talk about BOD5, that's the common. That means there are a lot of organic. COD. COD means, there are things that also dissolve, takes oxygen out. Mostly this has ammonia, nitrate, these nutrients. Because there or it could be other things, other chemicals. Actually, this is untrue. Nitrogen is also part of BOD because they also degraded by that. That's just a nitrogenous BOD. Okay. TDS is a total suspended solid, which is a amount of turbidity there. Suspended solid is another number. Oh, sorry, this is total dissolved solid. Dissolved solid means salt. This is a salt. This is suspended solid. So this is turbidity. That's how they measure, or how much particles stay suspended. That's what you have to remove by coagulations or mostly settling. And then we have nitrogen and phosphorus. These are nutrients. This is what I was writing here. And as you see, nowhere SS is a suspended solid. So this is written here. All the terms are written, what they stands for. As you can see, they don't really mention any specific chemicals. chemicals such as, like I said, now many chemicals are present in wastewater. PFAS, this is not regulated yet, even though it's there, because people just afraid to find out how much is there. So that's one. And PCB, all those chemicals that we expect in like fertilizers. Then many things used in urban areas. For instance, if you use paint, all those chemicals will leach into wastewater. So these are things you expect. Anything you use in urban area. So chemicals used in urban area. For instance, even though it's not recommended, many of us or many people actually throw their medicine into toilet. So that's actually a bad thing, because those chemicals are not, most of the time wastewater treatment plants are not designed to remove those to a very low concentrations. They remove some, but not as much as needed. So mostly what you should do is throw those into your trash, because then it goes to landfill, then it stays there. If you throw into your toilet, then obviously 90%, mostly nearly 90% will be removed. That 10% is still a very high amount. So that's why those wastewater is released to environment. All your stream water, everything has a lot of medicines. So that's big concern, because those hormones, those medicines, actually causing antibiotic resistance in our body. So that's why it's very important. If you are taking any antibiotics, do not throw into the toilet, throw into your trash, because now you are making everybody developing that resistance. That means those same medicine will not work anytime you get infections. Okay. So these are not removed sufficiently. So that's why they said don't dump into those things. Okay. But they have different processes. If they have to remove something, they have to add an activated carbon treatment system. So anytime they have to remove these kind of chemicals, they have to write granular activated carbon treatment. So they basically add that at the very end before disinfections. That way they can remove all these chemicals. But that's very expensive. So that's why they don't do it unless they're violating the law by having high concentrations. So what we are going to cover is everything, assuming there are not enough chemicals. So typical, again, these are the concentration. You can see they have 3 different ranges that are given. One is medium concentration. That's the average concentration you expect. As you can see, the BOD value is around 200. Okay, BOD 5. Notice I never give BOD ultimate, because in wastewater you don't really measure ultimate easily. What you do is you measure BOD 5 and then you extrapolate to BOD ultimate. So most of the BOD question in wastewater treatment plants will be given BOD 5. So first you have to turn into BOD ultimate before you solve these questions. Okay. All right. So now these wastewater treatment plants are designed, as I said, they have a law that made them treat this wastewater to a certain extent, and the goal is this. Their goal is the BOD 5 concentration has to be as low as 30 milligram per liters BOD 5. Okay, that's monthly average, because sometimes it goes higher, sometimes it goes low. They are not regulated by daily average, because daily there could be fluctuations, so they don't. It's too expensive to design something that low. So that's why they calculate monthly average. And if you do weekly, it becomes 45, because you want to be more strict. If you do daily, that will go a little bit higher. Okay, so this is that they do not normally weekly once, because as you know, the BOD 5 takes 5 days. Okay, so it doesn't make sense to measure BOD 5 every day. So that's why it's a weekly average. All right, so now that you learned the basic background, let's think of how to design one. Okay, and you already learned all this. So I'm just going to go over through the first thing. So let's start with the concept. You have raw sewage coming with all these pipes from different home. Then you get, the very first thing you do is, even the wastewater is 99% water. So raw sewage is, I would say, 99% water. Then you have solid. Then you have dissolved chemicals. That's roughly, and again, solid pathogens. So these are stuffs you have, right? And so you design the system such a way that you remove the things that are easy to remove first. Okay, so that's why you see this bare rack. Bare rack means, you have basically have pipes like rods like this, and water is flowing through that. Okay, so water flows through that so that you remove any kind of large particles. Let's say somebody dumped a big Coca-Cola bottles. This is where you can remove them. Okay, so it doesn't get into the other system. Then this has basically removing all the large particles with a certain size, not particle, like big chunk of stuff that floats, plastic, all that. Then you have grid chamber. Grid chamber, the idea here is that there are particles so large, small enough to pass through that, but because large, it might actually clog the system later. So what it does, it is basically crush all them to make it very small size, so that it doesn't clog the pipe later. So this is basically crush large debris, like wood chips. Think of wood chips that they'll go through those other things. You don't want to crush them. Then you have equalization basins. Basically, all those goes is just to settle things and all that. Once you finish that one, you go to primary. So this is basically pre-treatment. That's required for everything to remove the large particles. Okay. This is mostly particulates. Particles, debris. I think greater than 1 inch or bigger. Okay, roughly just remove those. The next thing is primary treatment. Primary treatment goal is just to settle particles, settle any heavy thing. So primary, when you heard primary, that's basically settling, gravity settling, which you already know by Stokes' law. So this is something we are not going to learn again. You already know those things. So, but this is basically settling. You know that one, why it is done. What is new here is this biological treatment or secondary treatment. Secondary treatment, the idea here is that it removes, settling will remove some particles and BOD, because there are particulate organic carbon, so those are also source of BOD. So any particles which has carbon is also source of BOD. For instance, leaves, those things will be removed. So this is BOD particles. Okay. And then next thing, what you have is mostly dissolved organic carbon. What comes from here is dissolved organics. That's getting into the biological treatment. So this is what basically your BOD is. Okay. And your goal is to remove those BOD in these units. That's called secondary treatments. And the way they remove it is exactly what we do in our body, digest them. So how do you digest it? What you do is you put some microorganisms so that they can start eating those BOD. And you know that that's possible. So you add microorganism, but microorganism is not necessarily, they don't have everything. What they have is just the food to eat, but they also need oxygen, because this is so high concentration. Dissolved oxygen will be so low, they can't really treat efficiently, because your BOD concentration is way higher in wastewater. And you know from the surface water that the BOD concentration is high, DO is so low that many things will not survive. So to make sure that this microorganism has enough oxygen, what you do is you add oxygen, aerations, okay? Basically bubble air through it. And so they have now oxygen, they have food, nutrients is already there in the wastewater, so they will just grow. So this is basically is called activated growth process, because you activate them by adding oxygen. Okay, so they are growing, now they are eating those BOD, and now what you have is, now you dissolve all the dissolved organic matters, or BOD is removed. What you got from here, biological treatment to secondary settling, is lots of bacteria, lots of microorganisms, which are produced because you are basically making them grow there. So now you don't want those biological organisms to get into your pipes. So what they do is they remove those all these microorganisms that treated the wastewater. So this is basically this remove BOD, but here you have lots of microorganisms that produce in this biological treatment get into this. That's why you have to remove them by settling. Okay, so that's why there is a secondary settling to remove biomass, all these microorganisms produced there. Once you finish that one, then your water is clean. The only thing that's missing is pathogens, because there are also pathogens. As you know, the restriction for pathogen is very strict. So that's why you have to have a disinfection here to remove pathogens. And if you really want to remove other chemicals, like I mentioned, for instance, PFAS, all these other chemicals that's really, very small concentrations, but still very high, you want to put activated carbon bed here to remove specific chemicals, specific regulated chemicals. But that's not 99% wastewater treatment plants do not have that one, because normally the wastewater treatment plants receive water which is not so polluted that it does, but occasionally it has. When it does, then they'll have to implement that, which they can just remove whenever they don't are not in violations. So as you see, primary treatments remove nearly 60% of solid. Solid means the particle that settles, and 35% BOD. So this number is relevant because in most of the example problems or exam question, you will be given what is the wastewater quality. So you have to remove 35% BOD from that before you calculate how much is getting into the secondary treatments. Okay, so because you need to know what's input to calculate what is output. So that 35% number is important. Okay, so you'll use that. Same thing for solid. So I already discussed this one. What I wrote there is basically the same thing. I didn't realize this slide is here. Normally I put this space to write it, so I kind of constrained it. All right, so now that you learned this one, let's have a quiz. Well, there is no quiz question here, but this is a typical quiz questions for the next quiz that's coming, last quiz. Identify the pollutants that are removed by different sections of the treatment plants. So that means you have given all these 5 different choices. You have to identify at what location what are mostly removed. Okay, and so this is something in exam question also you'll arrange it, or you'll drag it to BOD, you'll go to the place. For instance, I'll just give a answer just because we discuss. BOD, you just know that is removed by biological process in this this is BOD. Okay, so let me write 1, 2, 3, 4, 5, 6. So you have to just write which location what is being removed. So BOD is removed on number 3 locations. What about large debris or plastics? Any answers? 1. Yeah, so this is the one. What about suspended solid? Next one. 2. Okay, so that's 2 and 4. But mostly if it is bacteria, that's what's biomass, that's removed in 4. So that's the correct answer is 2. Biomass produced in the number 3 is going to be removed here at number 4. Where is pathogens are removed? 5. All right, so that's 5. Waste solids, something that I didn't really discuss. Basically, if you see your secondary sedimentation tank is removing all these biosolid or sludge. You have to remove them because you don't want them to be there. So some of them are recycled back because you want this microorganism to go back to the original treatment plants, because a lot of times wastewater doesn't have lots of microorganisms. So you have to put some of them back there. But most of them is go to sludge processing at the bottom. And also in the primary treatments, you have some solid settled. So all the solid get into sludge and use as a fertilizers. Because there are a lot of, basically it's microorganisms. So it's a biomass cell body. So it's a very high quality fertilizers. And so roughly 51% of those 51% of biosolids are used as a fertilizer in the US. Okay, of all biosolids are used as fertilizers in the US. Okay, so now at least you know how to answer this question in exams as well as midterms, or not midterms, the quiz. So again the quiz is next week, week 9. Okay, and that's the last quiz. Everything covered after the second quiz is going to be part of this one. Okay. All right, so how treatment system work? I really recommend you guys watch this one. Everything I just explained is explained here. Okay, but it's explained in a much better way. All right, so pre-treatments, I was going to show you how they look. As I said, the bare rack or grinder, this is where they crushed. Okay, this is where they move through. Those are the bare rack. If you see this location, all those area, water is just going to move through this like this. Somebody just take it up, and that's how it is. So looks okay, but it's inside the place. You have many of those line by line, so water moves through that. No water can escape from the side. So what it does, any kind of large particles get crushed. Okay. Pre-treatment grid chamber. This is basically like a centrifugal force, where what it does, it moves through water in a very circular motions. The way it moves, the basically it's a pipe where you inject on one side. So when it's moving, there is a centrifugal force. What it does, it makes the large particle escape from the. So that way it's moving. All the large particles will just squeeze into the wall and fall into at the bottom. Whereas water and the central line will be all clean, or at least less particles. There are different design. This is not just one way. There are many types of design. So those are removed. Again, you can read the textbook to see more about those if you want to understand. Primary treatments. This is something you already know. Primary treatments, how it's designed in drinking water. This is exactly same. There's no difference. Okay. So I'm just going to write the equations. You know the gravity, how buoyancy, gravity, and another one is viscous force. When it's combined together, you determine the particle velocity. So settling velocity is, can somebody remember? I don't remember. But that's particles density minus water density times d square. Gravity is on the up, right? Okay, and then you have 18 mu. Mu is viscosity. This is particle diameters. This is gravity. So What? Yes, density of water is constant. You can assume 1. So this is a way you can use, and then you compare with the overflow rate. If you remember what that equation is, overflow rate is flow rate divided by area, okay, area of the clarifier. So that the surface area, the top. So if it is circular, like this, I'm talking about this area. Okay. So that means all you are doing is you are comparing with the settling velocity with overflow rate. If the overflow rate is shorter than or equal to particle velocity, yes, everything will be removed. So basically, you're settling. You have to settle before you start overflowing. Okay, that's all it means. If your overflow rate it overflow much faster than the settling, then obviously you're not removing some portion. So what I can write is percentage removed is Vs divided V0 times 100. Okay. If is Vs equal to V0, then 100% are removed. Okay. If Vs is more than V0, obviously everything will be removed before even get to that exit. So this is something you already know. Let's just rephrase or remember everything what we learned last time by solving a question. So as you see here, we had drinking water treatment, so that was not part of the midterm. So anyway, this is also part of the finals. Okay. So you solved these questions before for drinking water. Let's solve it again. A town of 30,000 people spends 0.5 cubic meter of wastewater per person per day. So what it does, it gives you amount of wastewater produced by a different way. So 3,000 people, each person sends certain amount certain per day. Then you know that how much actually they send. So this is all about that. So this will give you the flow rate. A conventional circular primary clarifier would be designed to have an average detention time of 2 hours. So it says detention time. Okay, this is something. If you don't remember what is detention time, so this is theta. Theta is detention time. It's basically volume of clarifier divided by flow rate. Okay. So that means this because given that one, that means ultimately it gives you a volume. Okay, because flow rate is already given to you in this. An average overflow rate is given. Overflow rate is given. V0 is given as 40 meter per day. Every time you see equations, write what means in the symbols and write the equation that describe it. That way you know what is known, what is unknown. Okay. So overflow rate, you know the equation that describe it is basically Q by area of clarifier. That means if you know Q and know overflow rate, you know also the area. Okay, because everything else is given. And it says, whereas a high rate of clarifier would have average overflow rate is 1500 meters per day. So what you have designed is only 40 meters per day. But if you have a very high rate clarifier, you have to achieve that one. And you have to achieve that one by certain way. You know that based on this equation, you can achieve high overflow rate by increasing Q. But that you can't do it here because the amount of water that you receive is constant. That's based on how many people sending that wastewater. The only way you can change that one is decreasing the area. Okay. All right, so I kind of give you the context now. So what would be the dimension of the conventional clarifier? Dimension means it's asking the diameters as well as the height. Okay. So as you know, what is in all these equations, what is that area is given somewhere. If you know the area, you can calculate the diameters. And from that equation, Q over A The overflow rate, that's already given to you. So first you have to calculate Q. So let's calculate Q. Calculate Q is 30,000 people per person times each person is producing 0.5 cubic meter per person per day. Okay. Person cancel out, so you'll get a volume of meter cube per day. So that will be 1.5 times 1023. So let's see. Okay. So this, based on these equations, you know area equal to Q over V0. So if you know area equal to Q over V0, which is area of a circular area is basically pi d square divided by 4. Okay, that's the formula for a circular area. Okay, so that is pi db square divided by 4 is area equal to this, which is basically right 1500 meter cube per day divided by settling velocity, which is 40 meter per day. Cancel out, 1 meter cancel out, so you get the answer in how much? You already calculate? How much you said? 375. Okay, that's good. Okay, good. Thank you. Now I will always look at you every time I have a calculations. All right, 375 square meter. Okay. If you know this one, now you have to calculate dB. Is basically 375 times 4 divided by pi, 3.14, and then 21.20. Thank you. Now, second question was, what's the dimension? So dimension means doesn't mean the diameter, it also means height. So how do you get the height? From the volume, right? So let's write the volume. So volume is retention times hydraulic retention times time flow rate. So that would be 2 hour times flow rate is 15,000 meter cube per day. And obviously hour is not the same as day, so you have to change that conversion factor here. So you know that 1 day is 24 hours. If you do that one, the answer would be 1000. So 15,000 times 2 divided by 24. 1250. Yes. Oh, this meter cube. So if you know volume, obviously you know what's the height, because height would be, so let's see, we have space. Height or dB, volume over area. Right. So I'm just going to write 1250 Q divided by area is given or not, or we calculated somewhere. 375. So 3.23 meter. All right, so that's great. So this is the dimension. This is how you can calculate. So many questions in the final, also midterms, as you noticed, is always like this. You know, you will have something is given. If you write all the equations, you know what is unknown. You can derive that unknown there. In fact, I would say final would be a little bit easier because you don't have any mass balance to take care. You are not deriving mass balance equation, or you're not even checking mass balance. You are just looking for the equations to solve it, to write the answers. Okay. Okay, so number B, how much area would be saved by using a high rate clarifier? So it's basically how much area would be, what is the AB if overflow rate is 15. That's the question asked. Okay. So look for equation that has V0. So V0 is basically yes, Q over area. So that means area is Q over V0. So Q is 15,000 cubic meter per day divided by area is how much is 1500, not area, 1500 meter per day. Oh, that's very easy. 10 square meter. So you save around, before your area was 375 square meters. Now you all you have to take care is only 10 square meters. Okay. All right. So that's basically you know how to solve this question based on drinking water treatment plant. Nothing new here. What we'll do is I'll give you some concept before we take a mid break. So let's think of secondary treatments now, so that you know what's the concept we are going to use. Then we solve problems after coming back. So think of this, the secondary treatments. If you see in the very previous one, the only thing that's left over here is BOD. Okay, so the BOD, the organics that you want to remove, is what is left over before it goes to secondary from primary. And so those BOD can be removed by using microorganism. Basically, how you are eating food, this is basically you are giving this microorganism to eat all the BOD. As I said, that require oxygen. So what it does is remove BOD and it removes some suspended solid, because there is another clarifier, so it's going to remove that. How it works? Microorganism basically eat all this BOD. And in this picture, you see, this is basically bubbling air. That's why you see all these whites. Those are the foams. These are the airs that's coming out. In fact, 95% of the cost of wastewater treatment plants because of this bubbling air. That's the energy cost of running that pump for every day. Okay. So if you think of what's the most cost, that's the electricity of pumping that air. Okay. And so how to minimize that? Obviously, if you have waste heat or energy that is there available, then you can do that. And in fact, you'll learn in the next class that a lot of times people take these organics and do anaerobic treatment, where you basically produce methane gas. And when you produce methane gas, you produce energy. You're not using energy, you are producing energy. So in that case, wastewater treatment plants become a source of energy. Okay, we'll learn that next class. Okay, but some of the time, again, why people are not doing it, all of them, because of certain challenges. Like it has some limitations. It's operational in many places like San Francisco. In fact, there is one in LA. So what they do is they take all the food, all the restaurants, they have waste food. So they take those waste food and dump into wastewater. That way there are so much BOD that the anaerobic system is more efficient. Because BOD would not work. It requires anaerobic digestion will not work unless you have tons of food, because you need lots of organic to produce methane. Okay, so that so how much food you can get from wastewater is very little. The food means the BOD. So that's why to increase artificially, what they do is they buy, or not the buy, they basically all the waste, all the restaurants that donate those, not donate any waste food, they dump into landfill that produce methane and cause greenhouse gas emission. They take it from them, dump into this wastewater, create anaerobic digestion, and then they treat the water, and they produce energy and sell that energy. So many hybrid system, what they do is they have an anaerobic digester near the system where they use this food and all that stuff to treat them, and the energy that produced, they use it for this water treatment. So it's kind of, as you see, these wastewater treatment plants are becoming now energy neutrals or energy positive. So that's something we'll cover in the next couple of classes, where energy will come into your class. Now, so far we are just talking about water pollutions, not so much on energy, but anytime there is a concept, I'll just explain that. So what you need for secondary treatment plants, the very first thing you need is microorganism. You need lots of microorganisms to eat them, and eat them quickly. You need them healthy, you need them starving, so that the moment they see BOD, they will eat. Okay, that's number one. You need a good contacts of microorganism, because they are very tiny, right? So they are 1 micron or 2 micron size. They need to have access to those food. That way they become efficient. That means you have to mix them. The way to mix is basically when you bubble them, that's also served as a mix. Availability of waste, basically BOD, that's your wastewater treatment plants. Okay, that's the wastewater, the waste in wastewater. This is BOD. This one is by mixing. This one you have to produce locally, because naturally every wastewater has so much microorganism. We just have to grow them quickly so that it reaches that high concentration quickly. And then you need favorable temperature, pH, nutrients, carbon source, which is basically again BOD. Temperature, you can control too much. That's why in winter time you have to warm the wastewater before it becomes treated. Okay. No toxic chemical. This is another thing. If you have way too much toxic chemical, then obviously more microorganisms will die. So you can't use this treatment system. That's why you don't mix industrial wastewater, which has lots of toxic chemicals, with municipal wastewater. So this is not mixing industrial chemicals. So that's why it says do not dump chemicals into your sink. For instance, if you have chemicals that you just you can dump into there, that's basically violations, because they can't treat it. Okay. So good contact is basically mixing. There are different ways. So basically, as I said, the oxygen is basically suspended growth, because the microorganism is suspended, bubble is just rising, but there is a growth. There is a contact base where it's called trickling filter. What you do is you have basically lots of rock, and you just pour water slowly on the fountain. As you can see in UCLA, you have that fountain, reverse fountain. That's basically a trickling filter that also clean water as it moves through, because the oxygen helps mixing oxygen. So any kind of chemicals, BOD is going to be removed by microorganism. Okay, so that's basically a trickling filter. There is another where it's basically a big fan just moving inside the water. So the microorganism attached to the fan wall, and that's the basically contact growth process. So this is basically, there are certain terms that you have to remember. What are those? As you see, secondary clarifier, the word or come in. Mixed liquor means anytime you see mixed liquor, I don't know whether I say it correct way. You see the spell there, this one. Okay. The reason it's called mixed liquor is because it has both BOD plus microorganism. Okay. That's why it's called mix. It's not just liquid. It has a lot of other solid things. Okay. And microorganism growing. That's why it's called mixed liquid. And you have airs. Air is basically source of oxygen. That's why you're bubbling air. That also serves as a mixing point. Then everything is got treated, BOD removed, because that's now microorganisms eat them all. They grow. They have children. There's grows now. So basically, you have way too much microorganism in that. The next system, you are just basically using secondary treatment to remove all those microorganisms, setting them. So what you got here, this adding oxygen, this process is called activations. this whole process of adding oxygen is activating those microorganisms. Basically, if you don't add oxygen, they are dying or they are sleeping. The moment you give oxygen, they are just now activated, active and growing. So those microorganisms we call activated sludge. Sludge is basically gooey stuff that you don't want it anymore. So you see, this is waste activated sludge. Those goes to as a fertilizer after processing. We'll check how they do it next class. Okay, that's related to waste management. So this activated sludge is basically used as fertilizer, but some of them, because they are very enriched with lots of microorganisms which are designed to remove BOD, instead of producing them again, what you do is you basically take some amount of it and put it back into the aeration chamber. The reason you do this, that's why it's called return activated sludge, RAS. Okay, so this word. A lot of time the question is so long for this type of question, it's easy to get lost. So that's why I say these terms are important for you to remember. Okay, you know what is given, what is not. There are lots of pipes, lots of things going here and there. And the reason for return activated sludge is the natural wastewater do not have sufficient microorganisms to kickstart them, right? So that's why you are giving something back. And then activated sludge, that's how it's repeated. Okay. And the tertiary treatment system is basically disinfection process. We already learned it. Okay, so in those other classes. So I'm just rephrasing it before we come back after the break to work on secondary treatments. So tertiary treatments, you have EV, chloride, chlorine, ozones. Most people use EV or chlorine. Ozone is give a lot of few times you use ozone. Ozone is more reactive. Okay, and chlorine is added to for the distribution system. So go back to the drinking water treatment plants to learn what those concepts are. Basically, you want to use very highly, the very powerful disinfectant right at the treatments, but add a disinfectant which survive for a long time in the distribution system. That way, when you release that wastewater in the pipe for a long time, it is still disinfecting any bacteria or any pathogens that survive in those pipes. That's the reason you add chlorine. Chlorine survive long time. Ozones very quick. Within few seconds, all ozone will become oxygen. They react very quickly. So that means if you put ozone, you expect them to last in the distribution system, it will not last. That's why you use chlorine or hypochlorite or bleach. Okay, that's why sometimes in developing country, if you go to Bangladesh or India, you drink water, sometimes you smell chlorine. The reason is because of this. Okay. All right, so that's before break. So we'll have a 10-minute break. We'll meet at 1:05 to solve these questions and understand more on this. All right, so now we are going to understand more about the specific design of activated sludge treatments, the math behind it, so that we can solve this question. Let's see. Okay. So as you see, there are two systems here. One is, this is your activated tank. This is where all the action is happening. And then you have a clarifier. So these are the two notation I always keep writing. A square, which represent the activated tank, where oxygen is added. Okay, like this. And then you have clarifier. So that's where all the settling will happen. Okay, so microorganisms settle. And then some of them, you discard them, all the waste, the solid waste, you discard as this is basically sludge. Okay. And this is treated wastewater. This is from primary clarifier. Okay, so I just wrote all the so this is basically illustration of the when you simplify the math, okay, or the mass balance. So as you see over here, all it says is you have Q. Q is the flow rate that received from after the primary clarifier. And you have also some amount of BOD there, which is notation is S. S means substrate is BOD. So as you see over here, S stands for substrate or food, that's the BOD. Okay. And then you have also X. X is representing how much microorganism present or suspended solids or microorganisms particularly present in the wastewater. The reason is called volatile suspended solid is reason is how they measure that. Because if you think if you have large particles or soil particles, if you burn them, let's say you separate all the particles and you have some microorganism and you have also some soil or sediments. Those are, if you burn them at 300 or 400 degrees Celsius, all the soil will left behind. Any microorganism, they will turn into ash or carbon dioxide. Okay. It's like our body is volatile because your body will not survive heat, high temperature burning, but soil can. So that's why any microorganism mass they measure by just burning that filtered solid. That's why it's called volatile suspended solid. It doesn't mean that they are just evaporating or into air. When you burn them, it becomes carbon dioxide. So that's why when you see volatile suspended solid or VSS, then you know that it's talking about microorganism X. Okay, just remember this one because that's very easy to forget what's given, what's other. Return activated sludge, we just talk about it. So sludge has lots of volatile suspended solid. Okay. And then you have also lots of subscript, basically R for return or recycle. O stand for E stand for effluent. And this is basically input. Anytime there is a 0, that's input. So that's the notation. So that's why I write X0 here. X0 means this is the amount of volatile suspended solid in the wastewater that comes from primary treatment plant or primary treatment units. So let's walk through what happens. So those wastewater come in, it mixed with something that from the behind, from the back here. We'll talk about those. They got mixed. It's not necessarily they mix in a pipe. What they do is they just dump into that aeration tank. So in aeration tank, what will happen? Microorganism will grow because that you are providing them food and you are providing them oxygen. So this X0 will turn into, in this system, X would increase. Okay. That means you are producing more microorganism. So this X goes up in the system. But they are producing microorganism and they are also eating all your BOD. So the food, available food is going to decrease. That's basically your water treatment. You are removing your BOD. So S will, or amount of S0, the S value will be a lot less. It's decreasing. And then you have, this is volume. Volume of aeration tank. Okay. And then you have also the return activated sludge QR. So this is QR. QR means the flow rate of water containing those activated sludge. It has also concentration XR. That's the amount of microorganism you are putting back into the system. It has also some amount of substrate or BOD. As you can see, the BOD in this level is exactly same as BOD in the aeration tank. The reason is aeration tank, you remove all the BOD. After that, BOD doesn't get removed. Okay, so that's why the dissolved BOD remain constant after this one. So this S value is after treatments. This S value stay here. This S value also return back. Okay, that's the assumption because once the aeration tank, the BOD leave the aeration tank, it's not being used up anymore. So the value doesn't change that much. So now if you do mass balance, the two flow here, one is Q, another is QR return. So when it makes together, if you see the Q is coming here and the QR is here, it mixes together, the flow rate becomes Q plus QR. Okay. And then everything inside the reactor is what leaves the reactor. That's the assumption well mixed system. So that's why the concentration of activated carbons or activated sludge, not activated sludge, concentration of BOD is S. S is basically what is inside the reactor. And the concentration of microorganism or volatile suspended solid, VSS, is X. Then it goes to that second activated clarifier. So in the clarifier, what will happen? All the X, all the microorganisms, suspended solid, will no longer be suspended. So they are now settling. And so they settle at the bottom. So that means here, the X value would, in the effluent, will go up. So that become XR. Okay, because you are now settling and making the microorganism concentrated into the very small amount volume. So that's why your XR goes. Your XR here grows not because the bacteria is growing. The XR goes because you are concentrating. Okay, this is a concentration. This is not a total mass. All the mass, you are now concentrating them. So these are all small quiz questions. What happens? Why the concentration grow here? The reason is they are not growing. They are being concentrated by settling. But the BOD is not going to change. So that's why the S still remain the same. So now majority of this activated sludge, you are going to waste it or use as a fertilizer. So that's why the amount of activated sludge you use as a sludge as a fertilizer is QW. That's the volume of sludge that you have to remove from the system. XR is basically same as what is being concentrated on S. Again, as you see, there are many assumptions. The S is not changing once it's leaving the system. That's why I keep writing the same S. And if you see in the effluent, the S value is also same because primary the secondary settling tank doesn't remove any BOD. All it removes is the suspended solid or the microorganism. So the S value is same. So S equal to SE. Okay. And then as you see, whatever X come here, before the secondary treatment, this X come here, become concentrated, and then move as XR, which is very highly concentrated. That means what comes here, the XE has to be very small. That's the goal. You don't want the bacteria to go into wastewater, treated wastewater. So this XE value would be very low. Okay. So now if you write the equations or the comparison, XR would be very, very high concentration compared to X. And X is higher than XE. Just the order of magnitude to understand. Okay, the XR is the return activated sludge, they are concentrated. Same way, if you write S0 is greater than S. Okay. Because you are removing those BOD or treating the wastewater. Okay. So this is the concept, how things work. The math is easy because all you are doing is putting the equations, because I'll give you equation, you just substitute those numbers. So those are not difficult. The questions are not difficult. It's more about understanding what is given, doing what. So if I'm going to write the mass balance equations, so there is a quiz question here. So if you are solving for the activated sludge design, let's say this one, and this is your control volume, this is your control volume. Let's solve for X, basically saying that solve for X values. So again, you have one flow coming in, two flow going out. Okay, so sum of everything in a steady state, everything that comes in has to be what leaving the system, right? So what you can write here is the steady states is basically net change in concentration. So it's steady. Let's write steady state. That means dx by dt is 0. Okay, that's a change in concentration in the entire system is 0. That means you can write everything dx by dt is all in concentration coming in times flow rate minus concentration going out times the out plus volume and reactions. Okay. For steady state, it's basically 0. Everything coming in is only this one. This is the only one who is coming in, right? So you can write this one. The flow rate is Q. The concentration is, I'm just going to write X0. What's leaving the system is this 2. Okay. If you write that one, Q minus QW times XC minus was another output is QW times XR. Then here you have a reaction. The reaction could be positive or negative. Here, if you see this, you are writing about the bacteria. Bacteria is being produced inside the system. Okay, you are creating microorganisms in the system because of growth. So that's why this is a reaction is V, and this would be some growth rate times. Okay, so this is basically here. Growth rate is mu. So that's where bacteria are growing, right? That's where the reaction is happening. No bacteria produced in the settling tank. They are just being settled. They are not produced. And then you know that this is a first order. So this is normally expected as first order. So that means you can write how much amount of bacteria or microorganism produced inside the aeration tank is a growth rate times the concentration of bacteria available there. Okay. And this growth rate, it turns out it is also depends on how much food is there for bacteria to grow on. And that is, we learned that in the biology class, I wrote briefly, but I'm just going to remind it again here. So this is basically you maximum amount of growth rate times the food that available there. Then this would be so S is the amount of food and Ks is half saturation constant, something that you saw in the quiz, which is basically how much food is there that correspond to half of the maximum growth rate. We'll get to that, but that's the basically it. So when you write this equation and you solve it, you can solve for any unknown given to you. Okay, but you don't have to do that in exam because I will not ask you to solve any kind of mass balance. You know already the equations, and I'll tell you that next. So there is a quiz question here: why some of the flow from secondary treatment is recycled? The question is why this recycle happens. The reason is the wastewater doesn't have lots of microorganisms. So you want to have enough microorganisms to kickstart the process. So that's why you always recycle some of them. Okay, because wastewater has low, the X0 is too low for the production to start. The next one, we solve for this one. So why not we solve for now substrate? If you do the mass balance of substrate or BOD. If you do for BOD, let's do the same thing, exactly same process. Okay. So again, steady state. That means you can write that any BOD changes in BOD in the entire system. System is here the secondary treatment plants or this entire control volume. control volume. So anything inside the system where the net change in BOD concentration is 0. Okay. So that means you can write the same thing, steady state. So that's basically ds over dt system is again flow rate coming in times substrate that coming in, or everything in the input minus flow rate times substrate in the output plus reaction term, right? So volume times ds over dt reaction. Again, this volume is the volume of aeration tank because that's the only place your reaction is happening, not any other place. So if you write the steady state equation, that's going to be 0. Everything coming in is Q S0. S0 is input concentration of BOD minus this is one output, this is second output. Okay, this is one, this is second output. So if you write this equation, Q minus QW, another output, QW, then your reactions, volume time ds over dt. Okay, and you see that ds over dt is going to be it's basically saying that how much BOD is consumed for time, right? So this is your BOD equations. If you remember your BOD equation, it degraded at certain rate. That's KD. If you remember BOD equations, BOD ultimate is basically, or dBOD by dt is KD BOD. And the reason here the BOD is decreasing with time, so that's why you have to have a minus sign. Okay. But it's very difficult to measure the BOD utilization rate in this process. So a lot of times what they do is they calculate how much BOD is used up in the system by certain way. So what they will do is I'm going to write that equation somewhere. So this is all thing, it's over here coming. I don't want to explain very early. So just know that this is coming. And substrate, we already solved it, so I'm not going to write that there. But there is a quiz question here. We solved for substrate already, so we don't need to write it. Why do we need aeration tank? Why need to aerate it? Because you need oxygen. These are aerobic bacteria. They need to digest BOD, remove BOD by using oxygen as electron acceptor. So they means microorganism use it to digest BOD, which is equal to substrate here. Okay. So I already explained, I just want to reiterate again, all your process happening is your S0 is coming in, reaction happens, you have microorganism, and you have oxygen, you provide oxygen, those two in the aeration tank, what you got is S. Okay, the reaction is decreasing, so the S value is very small compared to, so S value is decreasing with time. Okay, that's your treatment is happening. And then at the same time, you have some X0 here, amount of microorganism initially present, and you add some of them together, so X0, and you add certain amount of other, because if you see how much microorganism present there, X0 times the, if you do mass balance, flow rate time concentrations, and then you add some other amount. So if you want to know how much of X coming here, this is the flow rate of wastewater treatment plants, and then you also add another, sorry, I see something I did. You add some recycle or return sludge times XR. And if you, this will become the net amount of microorganism you added, which will be whatever that amount. So it's basically Q plus QR mixed together times X. So this is X in. So the actual amount of X getting into the tank is basically this value. Okay, because you are mixing two different pipes. Okay, that's just the steady state. Once you put those here, they are now growing. Okay, so this X in is going to increase now. Okay, because so now this X in is increasing, X is increasing inside here because microorganism growing. So that means you can write X0 is turning in, or X in is turning into X. So what they do is they need oxygen, they need also substrate, the food. Those two together, mixing together, microorganism basically growing. And then you need to settle some of them because you don't want the microorganisms to grow. So that's how you do this process. So I mentioned this equation in the very beginning. How quickly this microorganism grow is determined by growth rate. So that's RG. G stand for growth. Growth rate. R for rate. So growth rate is basically dx over dt is equal to mu, which is a micron symbols. That's the growth rate constant time x, and there is no negative sign here because increasing with time. Okay, and this growth rate is a function of how much food is there. So that's the this is the process. So this is a called monod kinetics. Monod is a scientist who discovered this one, so that's why it's written. And so basically what you need to understand how's the growth rate, you need mu maximum, or the maximum growth rate. That's a function of the bacteria types you use in the wastewater. That's constant, means it depends on temperature, of course, but that's related to microorganisms. And the amount of food available, that's the wastewater. S is the wastewater that is in the aeration tank. So that's something you have to remember. Ks is half saturation constant, is basically Ks is the amount of substrate correspond to half of the maximum growth rate. This was a quiz question based on unit, so you already know this value. And then the substrate is utilized at certain rate, means the food or the BOD is utilized or removed at certain rate. That's basically ds over dt. What they do here is that this is a kind of change in equation certain way. So they multiply dx and divide dx, and it turns out this value or this value is a growth rate. This is equal to growth rate, and they define this term y, which is called yield. Yield means how much microorganism produce for removal of certain BOD. Why it is important? Because that determines how much waste you are going to produce that you have to deal with later. Okay, so this yield is very important. Your goal is to make the yield as small as possible. You don't want to produce too much sludge. That means you have to treat or you have to deal with those sludge later, right? So this yield is very important, and many wastewater treatment plants are designed to make the yield as small as possible. In fact, in anaerobic digester, your yield is 0. That means you don't want any, or not 0, very small. That's why you're not producing much waste there. We'll get to that later. But just know yield is dx over ds, and that number is given to you in a problem. Okay, though this is amount of micro, or let's say sludge. Sludge has produced to treat certain amount of BOD, which is ds. Sludge is dx. and this is usually given to in a problem. So if you plug this value, your KD or degradation rate that you know for BOD, okay, so this K value is basically BOD ultimate is BOD at certain time. So let's say BOD at any time. BOD at any time is BOD ultimate times e to the power minus KT. This is what the same equation that you use. So this is that K value. Okay. Before you used to mention KD. Here there is no other K, that's why you write K, small k. So as you see, this value is based on other rate. This is basically that number. So these are all just reorder of equations. Just know these equations so that you know what is not given. But this is all. There is what they're saying is that BOD is growing at certain rate, but they also die in the activated tank, because if you have too much microorganism, they will die at certain rate, and death rate is KD. So this is death. This is organism. So you are not only accounting for the microorganism to grow, they are also dying same time if you have too much. So you have to account for both growth as well as death. So net growth rate is basically how much rate that they are growing and how much they are dying. Okay, so when you combine them together, both rate, you get the net growth rate. Okay, so these are basically equations. You may not use it, just know conceptually. Okay, this is the net growth rate. And this is the finally, this is the what you need. Okay, this is mostly in the question they will ask you this question: what is the SRT? SRT is how much. This is the equation. Before you know hydraulic retention time. Hydraulic retention time is basically volume of treatment tank divided by flow rate. So if I ask what is the HRT here, HRT means hydraulic retention time. So that means that's the flow rate. Not flow rate, the volume of the treatment tanks divided by flow rate. Okay, and flow rate here is going to be Q plus QR, because that's the net amount of flow rate going through. That's hydraulic retention time. That's something you already know. Even in this clarifier, HRT is going to be, let's say clarifier volume is VC divided by the flow rate that coming into the system. So that's Q plus QR. This is clarifier. This is a aeration tank. Okay. So these are HRT. What about SRT? SRT is a sludge retention time. That means how long a sludge is remain inside the wastewater treatment plant. So as you see, this is where the sludge stays in this area. So I'm saying how long this sludge stays inside this system. So if you want to calculate that, you have to know how much the sludge is being coming into the system and the rate at which they are removed from the system. So what you do is basically total sludge. This is total sludge. SLUD produced total sludge removal rate. So total sludge produced is basically mass of total sludge produced, that's produced in aeration tank. So that's concentration times volume. So concentration of sludge is X times V. So another way to write is this is mass of total sludge produced by dm over dt. Okay, that's exactly what is written. So so volume times concentrations is total sludge V over X, because that's only place sludge is produced. And then your flow rate times the concentration is the rate at which they are removed. Okay, so that's written here. So remember this equation. This is the equation you are going to use to calculate SRT or any unknown value. So this is one of the question all the time in the finals. So this is one of the important equations. And sometimes you can also calculate XRT in different equation. You remember all the mass balance we wrote here? Mass balance for this. If you solve this equation, you can also calculate HRT. And that equation, by solving this equation, you will get this answer. Solving mass balance for X. In that equations and substituting all the things that you know, A, Y, and all that stuff, you will get these answers. But you don't have to derive it, you don't have to see how it is done, but just know this SRT you can calculate based on these equations. So SRT depends on the flow rate, yield. Yield means how much bacteria is produced per unit consumption of BOD, volume of the activated tank reactors, amount of activated sludge present, which is X. S0 is what is coming in, S is what is being removed. So the difference in the concentration of BOD. And KD is the death rate. Okay. So when you plug those all the value, you also get SRT. Now, why is important? Because a lot of times the question will ask you what is the SRT, and you will give in all this value. Sometimes some value is missing. For instance, many times XR is not solved for you. So you never know what is XR value. If you don't know that one, that means you cannot calculate SRT based on the first equation. Then you have to use this equation. So just know what is given, then you just plug the right question or right equations. The another times it says the food to microbial ratio in your activated tank, ratio in aeration tank, is basically how much food is there for microorganism for that. So how much food is there? Concentration times the volume or the flow rate, which is the food. Concentration is coming in is S0 times the flow rate. That's the amount of food you are supplying to this aeration tank. Okay, so this is food supply to aeration tank. That's basically concentration times the flow rate. An amount of microorganism present in aeration tank is concentration times volume inside the aeration tank. So this is microorganism in aeration tank. So a lot of times you are asked to calculate this value, you plug this question and you get the answers. And why it is important? Because the treatment depends on this. If you have too much food, less microorganism, they will take too long to digest it. If you have too less microorganism, too much food, that will take long. But if you imagine other way, you have little food, too much microorganism, you are wasting unnecessarily all these sludge and recycling, pumping them back, and then it's just you are not treating efficiently. Okay, so your goal has to have certain value of food to microbial ratio. That's why a lot of engineers or wastewater treatment plants engineer, they take some sample, always measure that food to microbial mass, try to maintain that there, and that way the reaction is efficient. They are not wasting lots of energy. Okay, so this is a question in the previous year final exam. So let's I'll not solve it completely, but I'm just going to identify all the numbers given to you, and then I'll always writing the equation, you plug the value. Okay. So as you see, this is a very long question. That's why it's very important to recognize this one. So this is again one question in your finals, and this is also a question in your homework question. So that's why it's a 2 question you get in this particular homework. A municipal wastewater treatment plant receives 3 million gallons of water per day. So what is given that one? Just based on that, the flow rate, okay, how much amount is coming in. So I'm just going to start writing somewhere. Q wastewater is given 3 million gallons per 10 to the power 6 millions gallon per day. That's given. Okay, so this is, I'm just going to write here, that's given. with average BOD5 concentration of 200 milligram per liter. So what's given in the wastewater BOD5? So I'm going to write here wastewater treatment plant. So this is a town, people, this is wastewater coming in. This you have primary, then you have secondary, then it's leaving. So this one BOD5 here is 200 milligram per liter. It's very important you don't write a different place, because then you know that there is a primary treatment still exists there. BOD5 is, and mind you here, this is given BOD5, not BOD ultimate. So the amount of BOD comes in, that means the, if you see, this is a Q in, you have to write what is X in and S in. Okay, how much substrate is there? That's BOD. So S, you know, BOD5 is BOD ultimate 1 plus or 1 minus. I think 1 minus K5. And BOD ultimate is basically amount of food is there. So that means this is, so BOD ultimate is S in, because S here is the food. Okay, the BOD is BOD5 times 1 plus minus 5 days. I'm just writing it here so that you know where it is. So S in, you know. Okay, that means I'm indirectly gave you how much BOD is there in the wastewater treatment, in the original wastewater. And you know, from the beginning, I said 35% of BOD is removed here. So that means you can use that to calculate what is actually coming into secondary, because you are always solving for the secondary, but all these things you have to do before. So that's why I just doing it in advance. It uses primary clarifier unit followed by a traditional activated sludge process. Activated sludge process is secondary treatment system to treat wastewater to maintain an effluent standard of BOD. So it means it says what is the effluent standard. So that means here you know S value here, S effluent is 10 milligram per liter. It basically say what is the effluent standard is. Okay, so you know what is SC, which is same as S. Okay, we write the assumption that. And it says suspended solid in the effluent. Suspended solid is same as activated sludge. All those things present same way. Is a 15 milligram per liter. These are all given. Okay. So I'm just going to write here. This is SC. Because bacteria also suspend, so that's why it's called suspended also solid. Assume that 30% of BOD is removed by primary clarifier. So here it's a 30% removed. %30 removed. That means you know what is the XE value is. So S X0 and S0, these numbers you need to know. So X0 is basically your, or S0 is 0.3 of S in. You already know S in, so you can calculate that value. So S0 is given to you because you already know S in. This is that. The microorganisms are 60% efficient at converting food to biomass. What is that number? That's a new term. How efficient they are changing BOD to activate the sludge. That's called yield. Okay, so the yield is written that way. So this is yield. So Y is 60%. And y is basically dx over ds. Okay, that's the yield value. So it's saying how much BOD you convert to dx. Have a first order death rate constant is this. So this is KD. Okay, that's the death rate. KD is equal to 0.5 per day or 0.05 per day. They reach half of their maximum growth rate when BOD concentration is 10 milligram per liter. That's the definition of half saturation constant, how the growth rate decreases half of this value. So this value is basically written, this is Ks. So K, half saturation constant, is you see a lot of numbers are given. Suspended solids were measured as 4,500 milligram per liter in a wastewater samples obtained from the biological reactor. So it says what is the suspended solid or the X value in the biological reactor, which is the aeration tank. So here it gives you the value of X is 4,500 milligram per liter. So X value is 45, saying that inside the reactor. And 12,000 milligram per liter in the secondary sludge. So that's the things that's being after the XR. So this is X, because after they are being recycled, all those things concentrated. 240 milligram per liter in the plant influent. So this is basically X in. So whatever the influent, X in 240 milligram per liter is basically how much is coming as a microorganism. And it says that 60% of the suspended solid, which is basically, you can assume these are microorganism, are removed in the primary clarifier. That means you have 240 milligram per liter and your X0 would be 60% of that. So that means your get X0 is 0.6 times X in, which is 0.6 times 240 milligram per liter. SRT equal to 5 days. So that's SRT. SRT equal to 5 days. And BOD decay coefficient, which is K, or is 0.2. So all this given, it says what is the value of this, estimate this value. Those are already I calculated. I give you that number. Calculate the volume of aeration tank. Just look at which equation has volume. Both equation has volume. It turned out I never give you this value or some of those value. So check, you can solve for volume if you just put all these other numbers, and those numbers are given to you. So you can put this equation and solve for volume, because SRT is given, Q is given, Y is given, X is given, this is given, this is given, this is given. Okay. And the last one is how many kilogram of secondary dry solid is produced. So that's basically how much of this is the dry amount of dry solid is being wasted, right? So this is, I am asking you this value, QW XR. So basically QW times XR is BX by, so this is the value is given. Everything else is given. And this is solve for equations on SRT. That long equations, this equation to calculate V. So as you see, these questions are basically everything given, you just calculate the value. So that's the question, all those answers. There is no other different way I can ask this question. So now you learn two questions. One is how to solve the hardness questions, and this is the second. So there are two long questions in this, and you by doing this example or this homework, you will know how to solve 2 long questions in the final. Okay. All right. Good luck. We are 3 minutes late.